Again, this is going in your lab journal. So what we discussed yesterday was we used the simulation to kind of check out what the different shapes were going to look like when we add one single bond versus two single bonds, one lone pair versus, two and some single bonds, right? So we got to see the different shapes. So when we were talking about polarity, we weren't talking about necessarily the bond polarity, which is where you are using your electronegativity values, back of the resource page. So if you open up your periodic table, you have your resource page in there. And if you look on this side, okay, it should be facing you because I tried fixing most of yours. But this is where you're grabbing those electronegativity values. When you subtract the two of them that are forming a bond, you're going to figure out what that difference is, and that will tell you a bond polarity. Molecule polarity is different. Molecule polarity is looking at the thing as a whole. So a thing that we said yesterday when we're saying polar and nonpolar on these notes was that polar, we're thinking not symmetrical. Okay, it's where we have a partially negative and a partially positive side. So you might add that to your top if I didn't make you guys do that yesterday. All right, so partially negative, partially positive. Those are just lowercase deltas. And then nonpolar would be symmetrical or balanced. So to kind of put this more in perspective, when we're dealing with polar and we have these partial things, it means that I'm not explicitly talking about a positive proton and a negative electron. Okay, we're not talking about that. We're saying partially. Partially, a good example of it is this picture, right, for water. So with water, basically what we see is we have this idea where we have been, when we're drawing our Lewis structures, we've usually put a dot, a single dot, and we connect them, right? So it doesn't really talk about one kind of leaning one way or the other, okay? Here in this picture, you're kind of seeing that those electrons are gathering a little bit closer to oxygen, meaning those electrons are leaning towards that. So therefore, you have a partially or more negative side and a more positive side. The other way to indicate it, and you guys being advanced, you guys are going to make sure you want to get comfortable with this concept because you guys have one additional part that you're going to start tomorrow with intermolecular forces, and it depends on whether a molecule is polar or nonpolar. Okay, so make sure you become familiar with that. You can kind of see that there's that partial picture, and you're going to be pointing towards the negative end always. Okay, so you'll have some practice, but let's get through the lab today. So the next thing, so then we went through each of these. So we had linear to start with. Linear, when there's only two, we depend on bond polarity, so that's subtraction. When there's three atoms present, like this, we're saying that if they are the same atoms on the outside, that is nonpolar. If they are different atoms on the outside, then that is polar. So when they were the same, a good example was carbon dioxide. Two oxygens, they're the same. If I had oxygen and sulfur, those are not the same. That's an example of each. The next shape that we dealt with was bent. So that was linear. Now we're on bent. Bent is when we have something with three atoms present and you have one or two lone pairs on the top. It just depends. Okay. When you have that, just like water, okay, this one is always polar. So I asked you yesterday to please put a star next to this one, right? So the reason I put a star next to it is because it's always polar, no matter what. You don't have to do any thinking. All right, and it's due to the lone pairs that are on your central atom. The next one you had was trigonal planar. Trigonal planar is when you have four atoms present and no lone pairs, right? So you have your three legs basically sticking out, and there's no lone pair on the center guy. So with that, you're going back to that original rule. If it's the same all the way around, so BH3, they're the same. BH2Cl is different. So nonpolar, when they're all the same. Polar, one is different. The next one we talked about was trigonal pyramidal. So trigonal pyramidal had four atoms present again, so it kind of was similar to this one, except now we have a lone pair sitting on the top. Because of that lone pair, this one is always polar, so put a star next to that one. This one you can rely on always being polar, so you don't have to really think about it. The minute you know it's trigonal pyramidal, it's a polar molecule. Okay, an example of that would be ammonia, NH3. All right, Tetrahedral was one where you have 5 atoms present. So now you have a central atom and then 4 sticking out of it, right? So this one, you have no lone pairs on your central atom, and it is not flat. So we're used to drawing our Lewis structures like this. This is methane. This is the one that we used during the Bunsen burner lighting. Okay, that's the gas that came out. And so methane, you know, when we were drawing it like this, we're like, oh, it's flat, blah, blah, blah. Now it's the 3-dimensional, it kind of looks like trigonal pyramidal, and then one is sticking up. Okay, so it is 3-dimensional. All right, so this one you are relying on whether they are the same on the outside or one is different. Okay, so here is an example of nonpolar, methane, and the polar would be even if you have 2 of the same, because this question, this comes up every year. I have a student who always comes up to me and they're like, yeah, but if I put the line of symmetry right there, then it's balanced. Don't do that, all right? It's 3-dimensional. It is not flat. So you can't put the line of symmetry there. It is not balanced. You have something that's different. Therefore, it is a polar molecule. Okay, so I just wanted to touch base on that. So those were the different shapes. Those were the rules to follow with your molecule polarity. All right, and that's what you're going to rely on for the lab today. So now let's go ahead and direct our attention over to our lab page. Okay. So yesterday we ran through this part, so hopefully you got all of yours drawn in. Okay, so they should have looked like that, right, after you tried them all out. Okay, this whole side, this is post-lab stuff, so don't do this until the very end, after you've done the other side, okay? Although you guys, I think I said I was going to check for a pre-lab, but we'll talk in a second. All right, so go ahead and flip this page over. I don't mind walking you through water real quick so that you know kind of what's coming. So if you don't mind going back to Schoology to make sure you have the simulation open. So I'm going to actually pause my recording real quick so that you guys have a chance to get that open. Get your simulation out or sit next to who you're going to be working with. Okay, all right, so the first one that we've got for water, on your simulation, basically what you should be on, as soon as you open that, this is what we were on yesterday, right, to do numbers 1 through 6. Go ahead and push on real molecules. So you should have this one on your screen, okay? And so what today is going to look more like is you have a drop down, and this will show you all these different ones. Now, I encourage you to look beyond what is on your paper, because some of these down at the bottom, these are your expanded octets. These are those other shapes, all right? So I will be giving you guys a handout of the other shapes, just so you know. But you are only held accountable for those 5, mostly. You guys might be asked like 1 or 2, but mostly those 5, so you're good. So we have our little shape here. Make sure molecule geometry is checked down on your bottom left. Make sure bond angle is checked up here in the top part, okay? If you change between model versus real, you will be changing your angle, just heads up. So I encourage you to just make sure if you're working with a partner, you guys are just at least on the same one. Otherwise, you're going to argue over the angle, okay? Okay, so for water, we're going to draw our model. So you're just going to draw the picture that you have. You could have moved it around to make sure it's pretty in your eyes and all that. So I'm going to go ahead and go, here's one lone pair, here's the other lone pair. All right, and if you choose to do the bubbles, that's cool. If you choose not to do the bubbles, that's up to you as well. All right, so here's my model. Then I'm going to look down here in the bottom left. It tells me the shape of the molecule. So that is bent. Bent. So again, I looked down here. Okay. All right. The next one is we're checking out bond polarity. We had to calculate electronegativity difference. So you should be using your sheet that's on your desk. Okay. Did I just? Oh, man. Oh. There it goes. Okay. So here's this. So oxygen, we're going to look for oxygen is 3.5. We're going to subtract hydrogen. Hydrogen's over here. It was 2.1. When I do 3.5 minus 2.1, I get 1.4. So that is your answer, okay? If I came up with a negative, if I had negative 1.4, what would I count? Absolute value, yeah. Just chop off the negative. Or if that really bothers you, then switch your two numbers to get a positive answer. All right, you'll be fine. So no negative answers in this column. All right, so at this part, you're going to be using this for deciding if the bond is polar or not. All right, now I was silly and I didn't add it to this one, so if you got a lab page from me today, you do have the spectrum, but most of you guys do not. So up at the top, if you don't mind writing in that little scale, you're basically 0 to 0.3, we're going to count as nonpolar. Okay, then 0.4 through 1.7, we're going to count as polar. And then bigger than 1.7, what are we going to count that as? Does anybody remember? It's the one where it takes the electron. Nope, with a metal and a nonmetal. Ionic, yep. So believe it or not, you will have one of your bonds on this page come out to be ionic. Does anybody have a guess on which one that is? Anybody see it? Mm-mm. It's going to be the one that has the metalloid, just so you know. All right. So you'll get an almost ionic bond, pretty much, is what you're looking at. All right. So now that we have those numbers, okay, for this bond polarity, you are looking at the scale that you just wrote in, okay? So we had 1.4. Where do I fall? Polar, exactly. We're between 0.4 and 1.7, so this will be a polar bond between oxygen and hydrogen. So the next one is molecule polarity. This is what was in your little half sheet notes. So you have to look at your notes. You got to pay attention to what shape you're dealing with, right? So we had the shape bent. What kind of polarity is that? Polar. It's always polar, exactly. So we're going to have polar. So again, this one is coming from the notes page. Okay? Finally, bond angle. You're grabbing from your simulation. So as you can see on your simulation, we have 104.5 degrees. And that's it. Okay? So it should not be overly difficult. You're just gathering a bunch of data, a bunch of information. I do recommend that you possibly work with a partner, like 2 or 3 of you can gather on your computer and work this out together. Or if you work alone, that's fine. Just make sure you're moving through it. Everyone is going to turn in what they finished today. When you are done with this table, flip the page over. You can start doing those post-lab questions, okay? It's back to drawing Lewis structures and recognizing what the shapes are. All right, so that